everyone, and welcome back to my online teaching platform. In this video, we shall consider the first application of differentiation. So we'd like to know the relationship between a straight line and a given curve. So when you say a curve, it means we are dealing with quadratic curve, cubic curve. So for quadratic curve, anytime you sketch the graph of a quadratic function, you are going to get a curve. When it comes to cubic, we are going to get a curve. But when you take a linear function, we are going to get a straight line. So we are to learn the relationship between the gradient of a straight line and the gradient of a curve at where the straight line meets that given curve. So we have here the first function to be y is equal to x squared plus 1. And the second one to be y is equal to 2x. So you could see that the first one is a quadratic function, so it's going to give us a curve. And the second one is a linear function, so we are going to get a straight line. Okay, now let us draw or let us sketch the graph of the two functions. So I'll start with the quadratic function. I'll be using this range of x values. I'll be using negative 2. So I'll be using negative 2, negative 1. So then I'll use 0 here. I'll use 1. I'll use 2 and also use 3. Okay. So these are our x values. So we are going to use them to generate our y value. So we are using a function y is equal to x squared plus 1. So to generate the corresponding y values, you plug in for every x value that you consider, you plug in that value. So I'm starting with a negative 2 as the x value. So I'll plug in negative 2 in place of the xy. So negative 2 squared will give us 4 plus 1. We are going to get here to be 5. The same thing applies to negative 1. We are going to plug in negative 1. So negative 1 squared will give us 1 plus 1 will give us 2. Then we move to 0. 0 will be plugged in place of x. So 0 squared will give us 0 plus 1 will give us 1. Now when we get to 1, 2, do the same thing. 1 squared will give us 1 plus 1 will give us 2. Then we take the second number of x, which is 2. So 2 squared will give us 4 plus 1, we are going to get 5. Then the next number is 3. 3 squared will give us 9 plus the 1 here, we are going to get it as 10. So these are the corresponding values of x for the given quadratic function. Okay, now let us consider the linear function, which is y is equal to 2x. So we are going to get a table for y is equal to 2x. So I'm using the same range of x values. Okay, so I'll use my x. I'll start with my negative 2, negative 1. You can use any range of x values, but I don't want to consider a range that will involve a lot of numbers. So that is why I've restricted it. So negative 2, negative 1, 0, 1, 2. Okay. Then let us look at how best we can go about it. So when I plug in negative 2 in place of the in place of the xy, we are going to get 2 times negative 2, and that will give us negative 4. When I plug in negative 1 in place of the x, it's going to be 2 times negative 1. That will give us negative 2. Now I plug in 0, I'm going to get 2 times 0. So that will give us 0. When I substitute 1 in place of x, I'm going to get 2. When I substitute 2 in place of the xy, I'm going to get 4. So these are the values of the y when we deal with the linear function. So let us now draw our graph. We are now going to draw the graph. So the origin is 0, 0, but let us consider the scale that to be appropriate. Looking at the scale, when you take the y values for the quadratic function, you can see that we have the maximum to be 10. and the least to be 1. So let us take the positive y-axis to be 2 centimeters to 5 units. So I'm going to use 2 centimeters to 5 units. Okay, so I'll start with my 5, then I'll move to 10, then the next one will be my 15. Okay, then when I come down here, I'll write -5, then -10. All right. Now on the x-axis, let's just use 2 centimeters to 1 unit. So here I'll write here to be 1, followed by 2, then 3. Okay, then we take the left hand side, the same thing, but it's going to be in negative form, -1, -2, then I have my -3 here. So let us get the quadratic graph first. Okay, let us work on that one first. So we start with the point. So we are going to plot the point. We are going to plot the x and the y coordinates. So the first part, we have -2 against 5. So we have the -2 over here against 5, +5. So it's going to be at this particular point. Then we move to the next one, which is -1 against +2. So -1 is here, then +2 will be somewhere here. Yes, okay. Then the next one is 0 against 1. So we on the y-axis, s is equal to 0. So we moved 1. Okay, so the 1 will be somewhere here. Okay, one step up. Then we move to the next one, which is 1 and 2. So on the x-axis, we look at the 1. So we have the 1 over here. We look for the 1. So 1 is here. Then on the y-axis, we look for 2. So 2 will be somewhere here. Okay. Then the next one is 2 against 5. So y is 5 and the x is 2. So 2 against 5 will be somewhere here. Okay. Then the last one is 3 against 10. So 3 here, then our 10 is here. Okay. So we can now draw our graph. We can now draw our graph. Let me change the. So this the graph for y is equal to x squared plus 1. Okay. So we write y is equal to x squared plus 1 here. Okay. Now let us look at the next one, the linear one. We are going to also work on the linear one. So the linear one we have here to be, we are going to plot a point -2 against -4. Okay, so -2 is here, and negative, so we move down because of the -4 of the y component. So it's going to be somewhere here. Okay, then we also plot the next one, which is -1 against -2. So -1 is here. Okay, this is a -1 against -2. So it's going to be somewhere here. Okay. Then we also have here to be, we are going to plot it. We have 0 against 0, so it's going to pass here. So it's going to be at the origin. Then the next one is 1 against 2. So 1 is here and our 2 will be here. Because this is 2. So x is 1 and y is 2. And the next one is 2 against 4. X is 2 and y is 4. Okay, so it will be somewhere here because this one is 5, so the 4 will be somewhere here. Okay, so we can now draw our x. Sorry, we can now draw our linear function, the graph for the linear function. Okay, so let us look at that one too as well. So we are going to draw it. Okay, so you can see that the linear function touches the quadratic function at this particular point. Okay, so at the point where x is equal to what? 1. At the point where x is equal to 1 and y is equal to 2. All right, so when you trace it to this point, look at it carefully. So this is where we have, so this is the y and this is the x. So at this point, we have it as 1, comma 2. So that is where they meet. So the graph for the quadratic function and the linear function meet at the point with coordinate 1, comma 2. All right. Now you could see that the line touches the curve at that particular point. Okay. So anytime you have a straight line touching a curve, that touches a curve at a point, just at one point, that line is termed as a tangent. Okay. So in this video, we can say that the graph linear graph is a tangent to the quadratic curve. Okay, so the line that we have drawn is a tangent to the curve y is equal to x squared plus 1. Okay, so this is our y is equal to 2x. So you could see that the y being equal to 2x touches the y equal to x squared plus 1 at the point with coordinate 1 and what? 2. X being 1 and y being what? 2. All right. So let us look at how best we can get their point of intersection without plotting any point. Okay. So if you know their if you want to know their point of intersection, you just solve these two equations simultaneously. So let us look at how best we can solve them. So we work on it here. Let us look at it carefully. So if I have x, I have y to be equal to x squared plus 1, and I also have y to be equal to 2x. You can solve this equation simultaneously to get their point of intersection. See where they meet. That is where the curve touches, or where the line touches the curve. We have it to be a point with coordinate 1 and what? 2. But let us use the simultaneous approach to determine whether the answer will be the same. Okay. So we have our function, the first one to be x squared plus 1, then another one to be y is equal to 2x. So we can name this one equation 1 and name this one equation 2. All right. So two things that are equal to the same thing are equal to what? Each other. So since y is here, y equal to x squared plus 1, and you have another one to be y is equal to 2x, we can replace, so we can put y equal to 2x into equation 1. Okay, so we are going to get it as 2x is equal to x squared plus 1. And this will give us x squared minus 2x. We transpose the 2x to the right hand side. Plus 1 all equal to 0. So we are going to solve this quadratic equation. Okay. Now we need to get two factors that when you multiply, you get positive 1, because the coefficient of the x squared is 1. So 1 times 1 will give us 1. Sorry, 1. So we need two factors of 1. Now when you multiply, you get positive 1. But when you add, you get negative 2. So the factors are negative 1 and negative 1. So negative 1 times negative 1 will give us positive 1. Negative 1 plus negative 1 will give us negative 2. So we are going to get x squared minus 1 minus what? Another 1. So if you don't want to do it this way, this is the best way to go about it. So we are going to replace the negative 2 with minus 1, or negative 1 minus 1, which is the same as negative 2. So negative 1 minus 1, then you bring your x here, this x. plus 1 equal to 0. Then we expand this bracket. We are going to get x squared minus x, then minus another x plus 1 equal to 0. All right. So this is what we are going to do. We factorize by grouping. So we are going to put two terms in one group. So we have x squared minus x in one group, then plus negative x plus 1 also in another group. Okay. We identify the highest common factor, which is the x. So x divide x squared, we are going to get x. X divide x, we are going to get negative x, we are going to get negative 1. Then here to the highest common factor is negative 1. So negative 1 divides negative x will give us positive x. Negative 1 divides positive 1 will give us negative 1. Then all equal to 0. Now we need to reverse what we have here. So we are reversing what we have here to get it as a binomial multiplying another binomial. Okay, so this become, we are going to put the factors outside in one bracket. So we have x minus 1 in one bracket. Then repeat one of the equal bracket. Okay, then multiply x minus 1 all equal to 0. Okay, so we are going to get x to be equal to positive 1. Okay, they are all the same. X minus 1 equal to 0 give us positive 1. Then we now put the value of x. Put x to be equal to, put x equal to 1 into any of the equations. So I'll use equation 2. I'll use equation 2, okay? So I have my equation 2, which is the y equal to 2x. So this implies that y will be equal to 2 times 1, which is equal to 2. So you can see that we have the two values to be, we have it as x, y to be equal to 1, 2. All right, which is the same as what we got when we use the graph. Okay, let's just look at it. The points are the same. Okay, now our focus is on how to determine the gradient of the curve. Okay, for a linear function, how to determine the gradient of it is not difficult. We just need to compare it with the general form of writing a linear equation. Okay, then you pick the m to be your gradient, which is the coefficient of the x. So in this video, our focus is on how to determine the gradient of a tangent to a curve, okay, and also determine the gradient of the curve at where the curve meets the straight line. So the straight line here is what we are calling the tangent, or what we term as the tangent. Now, let's just look at how we can find the tangent, okay? Sorry, I'm saying the tangent. How we can find the gradient of the tangent to the curve. Now we have our equation to be the curve to be y is equal to x squared plus 1. Then our line to be, our straight line to be 2x. Now let us find the gradient of this line and see what will happen. We just compare it to the general form of a linear equation, which is y is equal to mx plus c. Then we see that the gradient here is the m, so we are going to compare the coefficient of the x. So the coefficient of the x here is also 2. So we conclude that our m is equal to 2, which is the same as the gradient. If we could recall, in one of the videos under how to determine derivatives of a given function using the first principles, we learned that whenever you differentiate a linear function, whatever you get becomes the gradient of the function. Okay, but when you differentiate a quadratic function, a cubic function, you are going to get a result in terms of x again. You are not just going to get a number. So that result is what we call the gradient function. Okay, when it comes to quadratic and cubic, when you differentiate them, you are going to get your gradient function, not the gradient itself, or rather a gradient function. So you need a number that should be put in place of the x to get the gradient as a number. Okay. Now you can see that the curve y is equal to 2x. This curve and the curve y is equal to x squared plus 1 and the line y is equal to 2x meet at a point. They meet at a point with coordinate 1 and what? 2, where 1 is for the x and the 2 is for the y. Okay. Now let us check if we get the same gradient for that of the curve. Now we know that when you differentiate the curve, our curve is y equal to x squared plus 1. So let us find our dy dx. Okay, our dy dx will be 2x. Okay, when you differentiate this one, we are getting 2x. Now this is also the same as a gradient, but it is a gradient function because we still have x here. We still have what? X over here. But when you take the first one, which is when you have y is equal to 2x, which is the line. When we find the derivative, we are going to get dy dx to be equal to 2. And this 2 is the same as the 2 that we obtain over here, which is the same as the gradient of the given line. Now we have to find the gradient of this curve at where it meets the given line, y is equal to 2x. Okay. Now we have differentiated the curve and we had the result to be 2x. But we just need a value to represent the gradient, not an expression in terms of x again. Now, since they meet at a point, you need to now substitute the point of intersection into the gradient function in order to determine the gradient of the curve at where it meets the tangent. So let us verify and see if we'll be able to get a gradient of the curve at where it meets the line. So to find the gradient, we know our gradient to be dy dx, and we have the answer to be 2x. Now, they meet at the point 1, comma 2. So we know our x to be 1 and our y to be what? 2. All right. So this is our y. Now, in this gradient function, there's no y. So we only need the x. So let us plug in the value of x and see what we'll be getting. The answer here is also 2. So you could see that the gradient of the curve at where it meets the tangent is the same as the gradient of the given straight line. Okay, so we conclude that anytime you have a curve and a tangent or a straight line touching the curve at a point, the gradient of that line is always the same as the gradient of the curve at where they meet or at where the line touches the given curve. All right, so let us go back to our graph. Okay, so this is the point of intersection. So at this point of intersection, let us put P over here. Okay, so we conclude that the gradient of the tangent, okay, the gradient of the tangent, which is the straight line, is equal to the gradient of the curve at the point P. Okay, at the point P, and we can verify. When you differentiate to find gradient, is the same as dy, change in y with respect to what? Change in what? X. Okay, so we are going to determine change in y with respect to change in what? X. Let us look at it. So we are taking the linear function first. Y is equal to 2x. So dy dx is equal to 2. So this becomes the gradient of the straight line. Let us determine the gradient of the curve and see. So we have y to be equal to x squared plus 1. So our dy dx will be equal to, we are differentiating the function with respect to x. We are going to get 2x. Okay, this becomes our gradient function, but not the gradient itself. Now, so it means at the point of intersection, the gradient function of the curve at any point is what? 2x. But our focus is on the point of intersection. So we want to find the gradient of the curve at where the curve touches the straight line. So we are going to plug in the point of intersection in place of the x in the gradient function. So at the point of intersection, we have 1, 2. So 1 goes for x. So our dy dx for the curve at where it touches the line becomes 2 multiplying the value of x. That is the value of x at where the curve touches the straight line. So this will give us the result to be what? 2. And you could see that the gradient of the line and the gradient of the curve at where they meet are what? The same. So anytime you are answering any question on this and you have been given the point where a line touches a curve, okay, you have been given a point where a line touches a curve, and you have to find the gradient of the curve given the function of that particular curve. The only thing you need to do is to differentiate the curve to get the gradient function. When you're able to get your gradient function, then you now plug in the value of x at where the curve meets the straight line or touches the straight line to get the gradient of the curve at that particular point. And we know that the gradient of the curve at that particular point is the same as the gradient of the straight line. So if you are able to get the gradient of the curve at that point, you use that same gradient for the gradient of the what? Of the tangent to the given curve. All right. So let us conclude here. So let us conclude. So if if a line is a tangent, if a line is a tangent to a curve, let's say y is equal to f of x at point A with coordinate A, comma B. Okay, if A, sorry, I'm saying A. If a line is a tangent, this is the idea, this is what you are focused. If a line is a tangent to a curve, y is equal to f of x at point A with coordinate A and that of what? B. How do you determine the gradient of the line? That's what we want to know. So the gradient of the line will be, so the gradient of the line, gradient of the line will be equal to the derivative of the given function. So we are going to differentiate the given function, and that will give us the gradient function. So when you are done with this, then you plug in the x component. So the x component of the point where they meet is A. Okay, so the gradient of the line will be equal to f prime of A, meaning you are going to differentiate the function. Then after that, you plug in the corresponding x value of the point where the line touches the curve. Thank you for watching. In our subsequent lesson, we will be learning how to answer questions that involve application of a line touching a curve and also a line that is perpendicular to a tangent to a curve. So any line that is perpendicular to a line that is a tangent to a curve is called a normal. So in some of the videos that we'll be looking at what a normal is, a normal to a tangent is. Okay. But before I end this video, let us look at the normal when you are dealing with a normal to a tangent. If you have a curve and you have your tangent to the curve to be, let me use this one. If I have my tangent here to be, okay, so let us assume I have my tangent here Okay, so it is a point of intersection. So this is the tangent. So this becomes the tangent to the curve. Okay. Now, if I have another line which is perpendicular to the tangent, okay, let me draw another line over here. Okay. So this is my x-axis, this is my y-axis. So we have a line here which is perpendicular to the tangent. Okay. So this line is what we call the normal. This is the normal. A line perpendicular to the tangent of a curve is called the normal. So let us determine the relationship between the gradient of a tangent and the gradient of the normal. We learned in commerce that the gradient of two lines that are perpendicular, the product of the gradient of two lines that are perpendicular must give us a result of -1. So if the gradient of the tangent is m1 and the gradient of the normal is m2, it implies that the product of the m1 and the m2 must be equal to -1. So if you know the gradient of your m1, to get your m2, you just take negative reciprocal of your m1. So we can say that our m2 will be equal to negative reciprocal of what? M1. Okay. So this is how we go about it. So in our subsequent video, we'll be answering more questions and we'll be applying what we just learned. Bye. And thank you for watching.